All right, so let's look at how we would program out binary search in Ruby here and achieve a O of log n runtime for searching through a sorted array instead of our O of n linear search that would be some of the methods that are built into Ruby. So let's start by creating an array. So I'll call search array and set that equal to array.new. And I want some array size here. And the reason I'm going to keep that in a variable is because I want to reuse that size. So I'm going to say array size is equal to, we'll start out with 1,000. Okay? And we'll say array size is equal to 1,000. And I'm going to reuse that by making a random number generator here with random.new. And inside of this array of size array size, we're going to populate it with r.rand of that same size. And the reason I want to do this is because it gives me a good probability that if I'm looking for some number inside of that range, so I'll say my search num is equal to r.rand of that same size, I now have a pretty good probability that that value is inside of the array, but I also have a okay probability that it's not in that range. So now I can, if I run this multiple times, I can see a worst case scenario where that number is not found with a relatively high probability, and then I can see a non-worst case scenario where that number is found with a relatively high probability. So let's start by just testing out the Ruby index method. So I'm going to say puts Ruby index, and what index does, it's an O of n linear search algorithm where it goes from left to right to find some element that you're searching for, and then it spits out the index at which it found that element. Now, if it doesn't find it, it gives you nil. So I'm going to say result of the index method is equal to search array dot index of my search num, and I'm going to put out remember, so I have two options here. Resi is either going to be nil if it can't find the element in the array, or it's going to be some index number. So I'm going to put out two different things based off of which one I get. So if resi is nil, I want to put out could not find, and then I'll interpolate in here search num. However, if resi is not nil, okay, so if I do find that element, I'm going to say found, and I'm going to interpolate in search array at index of resi at index, and then I'm going to interpolate in resi. All right, so, and the reason that I'm doing this instead of putting in search num is because, let's spell this correctly, because I want to make sure, now with Ruby index I don't have to verify this, but I want to make sure when I start writing my own methods that I actually find the right number. So I'm going to be verifying. Let's go ahead and put out the number I'm actually looking for. Puts out search num. Looking for, interpolate in search num. Okay. And now I'm going to be able to verify that search array at index resi is actually the same number as search num. And that will help me validate correctness of my function in the future. So let's run this real quick and see what it looks like. One thing I want to do before I actually even run this one, so I'm going to go ahead and sort this search array, because to use binary search, this array has to be sorted. All right. So I'll say Ruby binary search.rb, and all right, looking for 234, could not find 234. Let's run it a few times. All right, and there we go. Now it's looking for 745, and it found it in index 764. All right, so it looks like that's working pretty well. So let's start a binary search implementation and try to achieve this search in O of log n time. All right, cool. So the two ways I want to program this out today are iteratively and recursively. And if you haven't worked with recursion before, it'll be a nice little introduction. We'll talk about how it works. But I want to start out with the iterative solution, because if you haven't worked with recursion, this is going to be a little bit more intuitive. And also, in my opinion, it's a better solution because it'll use less space. And we'll talk about that in the future. So let's go ahead and say def binary search iter. And I'm going to have to take in the array and the element that I'm looking for here, because I'm not going to monkey patch the array class. So I could use it like this. We're actually just going to make it a standalone function. So we're going to have to now figure out how to perform our binary search algorithm iteratively. So if you remember from the lecture previously, the way that binary search works is like you're going through a phone book, right? So I'm going to open up my phone book to the middle, see where I'm at in the alphabet, and then either attack the left or the right-hand side of the phone book, and then keep doing that over and over again, continuously dividing my problem size in half, so I don't have to look through every single page of the phone book, right? So I want to look at the very center of my array and decide which half of the array to continue to search. And then if I go to the right-hand side, for example, I don't then search the entire right-hand side of the array. I then split that portion of the array in half. Now I have an array subset or a subarray the size of a quarter of my original size. And then I divide that in half and then divide that in half. And that's how that continual dividing my problem in half is how I achieve that log n runtime. So I want to keep track of what portion of the array I care about because it's going to keep changing. It's going to keep honing in on some smaller subarray. So to do so, I'm going to keep track of the maximum index I care about, which is going to start off at array.length -1, and the minimum index I care about, which is going to start off at 0. Okay? And then what I'm going to do is I'm going to continuously look in the center of that array portion that I care about and either return something because I found the correct answer or redefine the min and the max values to hone in on the portion of the array that I now care about. So I'm going to have some while loop, and I have to now determine what makes this while loop break. What would happen that would stop me or let me know that the thing that I'm looking for is not my array? Well, if I'm continuously changing my max and my min values to hone in on smaller and smaller portions of the element will not be in the array once my subarray size is 0 or negative. So as long as my minimum value is less than or equal to my maximum value, I want to keep looking. Once my minimum value becomes greater than my max or my max becomes less than my min, once that happens, I know that I have no more subarrays, right, subportions of my array to look through, and I'm done. In which case, I want to just return nil. Nope, can't find it. All right, so now while I'm continuously changing my min and my max, I want to define, every single time I go through this loop, what's my procedure? Well, first of all, I want to calculate the midpoint of this array because the first thing I want to do is look in the center of it and determine if what I'm looking for is in the center. And if it's not what I'm looking for, then I'm using that center point to make a decision of whether to hone in on the right or the left-hand side of my array. So I'm going to start off with my min is equal to min plus max over 2. And let's actually take a break right here to make sure that this is correct. Look at some concrete examples. And we'll start off really small, very, very small arrays with a length of 1. And then we'll slowly make it bigger and make sure that that little calculation works and do basically an informal mathematical induction to prove that this is correct. So right now, my midpoint calculation is min plus max integer divided by 2. So in Ruby, that division, and let me go back real quick. In Ruby, this division right here, if I'm dividing two integers, it actually does integer division. And what that means is that it's going to chop off any decimal point. It's not going to care about it. It could be 3.999999999. Doesn't matter. It's going to chop off all that and just give me back 3. Okay? And that's going to be useful for us here because it's going to give us whole numbers, which is what we want when we're looking at indices of an array. So if I have an array of length 1, my min index that I care about will be 0, and my max will be the length minus 1, which is also 0. So my midpoint calculation would be 0 plus 0 divided by 2, which is 0, which means that I will look at element 0 first, which is perfect because that's the only one there. Perfect. That works. Let's look at length of 2. So I can't evenly, I can't evenly divide up an array which is of even size, right? So 2, 4, 6, 8, etc. Because as you can see, there's no element in between these two elements. So for every evenly sized array, I have two options to split it down the middle. And it's going to be between one of two indices. In this case, it could be either one of these indices would be valid choices because I can't split it down the middle. So kind of renders this calculation like not necessary. As long as I get 0 or 1, I'm good to go. So min will be 0, max will be 1. 0 plus 1 over 2 is 0, so I'm going to look at index 0 here, which is just fine. Now when I go to an array of length 3, I now want to make sure that I'm hitting this index right here. Okay, that's the only viable solution for my mid calculation. So my min is now 0, my max is now index 2. 0 plus 2 over 2 gives me index 1, which is in fact this one, so I'm good to go. Let's do one more, and then call it satisfied. And then actually really quick, we'll actually look at when our min is not 0 to make sure we feel comfortable with that portion of the calculation as well. So 0 to 3 would be my min and max. 0 plus 3 divided by 2 gives me 1.5. However, doing integer division gives me just 1. I will also look here, which is just fine. I'm just breaking up my array with 1 on one side and 2 on the other side, which is fine. All right, so let's add 2 more indices and do a few calculations where let's call my min 2 right now. So let's make sure that this calculation still works when my min is not 0. So here my min is 2, my max is 5, 2 plus 5 is 7, integer divided by 2 gives me 3. Index 3 will be a proper division between this subarray, putting 1 index on one side and 2 indices on the other side. That's completely fine. And then the last thing I want to check is when I have an actual evenly divisible one, if it goes in the middle. So index 2 plus index 6 is 8, gives me index 4 overall, which evenly divides this subarray perfectly. So I feel pretty good about this calculation. I think it's a good way to calculate the midpoint of the subarray, which we care about. And so I'm basically just taking the average of min plus max, or sorry, of min and max by adding them and dividing by 2. And now I'm saying, okay, so if the array at the midpoint, if that's equal to the thing that I'm looking at, I'm done. I return that index mid. And now what I have to do is define what I do if those two things are not equal. So do I want to look at the right-hand side of the array and discount the left-hand side, or look at the left-hand side and discount the right-hand side? So let's go ahead and say else if the array at the midpoint, if that's greater than the thing that I'm looking for, so when I look at the center of my array, if that value is greater than the thing that I'm looking for, that means I need to discount the right-hand side of the array and focus on the left-hand side of the array, right? Because the thing that I'm looking for is smaller than the midpoint, so I need to look at the portion of the array where things are smaller than the midpoint, which is the left-hand side. So if the thing in the center is too big, then we want to focus on the left-hand side of the array. So I want to redefine my max variable. Okay, so instead of the max looking all the way to the end of my array, I only want to focus on the things less than the mid. So max is now going to be mid minus 1. That's the maximum index I care about now. Everything to the right of mid is no longer a possible location for my element that I'm looking for. And then finally, my else here will capture the only thing left logically. So I've covered if they're equal. I've covered if the thing I'm looking at is greater than the element I'm looking for. So the only thing left is that the thing in the middle is less than the element I'm looking for. So if the thing that I'm looking at in the center is too small, that means I need to focus on the portion of the array where things are larger, which is the right-hand side of the array. So I now redefine my min point to be mid plus 1. Okay? And that should be it. All right, so I have a return value when I don't find it at all. I have a return value when I do find it. And I have things that change the condition of my loop to push it towards breaking, right? So I'm breaking my loop, that is, right? So I need to make sure that I'm not in an infinite loop. Well, every single iteration, I either return an answer, which gets me out of the function completely, or I lower my max value or raise my min value, which is pushing me closer and closer to breaking this loop. And so eventually I'm either going to break the loop, return this value, or return no. All right, cool. So let's give this a shot. So I'm going to put a put statement here at the bottom just to give me some space. And now I'm going to, let's just copy these 3 lines of code. I'm not a big fan of copying, but we'll do it today. And now we're going to look at binary search iterative, and this is O of log n. So now the result of binary search iterative, resb, is going to equal binary search iterative, and we're passing in search array and also search num. Okay, and resb, if resb is nil, we couldn't find search num. Otherwise, we found search array at index resb at index resb. Cool. Let's run this and see if it's correct. All right, so let's put another put statement right here so it looks nicer. But it looks like we have we found the correct number at the same index. Now note that we might not find the correct number at the same index every single time. If there are duplicates in search array, which there very well could be because I'm using a random number generator to populate it, then because of the two different ways that binary search and linear search look through the array, so linear search is going to look from left to right, and binary search won't do that. So I might find the correct number at a different index that this finds it at, and that's completely fine. It's still a correct solution. So as long as this number is the correct number, then it won't matter if these two indices are different because it means I still found an index with that valid element value inside of it. All right, cool. Let's run it a few more times to make sure that it's working well. 36 and index 31, could not find both of them. Okay, and here we have an example of what I was just talking about. So we found 368, which is what I was looking for. We found them at two different indices. And we found them at consecutive indices, which makes sense because our array is sorted. So looks like everything's working just fine. So let's go ahead and implement a recursive solution to binary search and to show you guys how we could do that. So def binary search recursive, we're going to have to take array and element here as well. And let's quickly talk about recursion if you haven't dealt with it yet. Now I'll probably do a whole video on recursion, so I don't want to get too deep into it. But basically what recursion is when I use a function that calls itself to solve a problem. So the goal of recursion is to break a problem down into smaller and smaller pieces until the problem is so small that it's very easy to solve. And then I use what we call a base case to solve that very easily solved subproblem. And then when I return from that base case, my recursion basically chain reaction returns up, solving larger and larger versions of that problem. Okay? And I do so by calling the function within itself. You can kind of think of it like Inception, when you have a dream within a dream within a dream within a dream. We have a function call within a function call within a function call. And every time I call my function, I'm having it solve a smaller problem until the problem's so small that I can solve it easily myself with code inside of the function, and that's what we call a base case. So just like we have when we had a while loop here, we had to make sure we didn't infinitely loop by continuously changing the things in the correct direction. In this case, min and max, we're continuously changing those to make min larger and max smaller, and then so by the nature of the code, we would be moving towards this breaking criteria. In the same sense, we have to make sure that we don't infinitely recurse and just keep calling our method over and over and over and over again. So we need something to make sure that we have that the lowest level dream eventually we wake up from, so we can wake up from all the other dreams, right? So the two times when I would want to have a base case, so I actually need two base cases here. I need a base case capturing the situation where the thing that I'm looking for is not in the array, and then I have to capture the situation where the thing that I'm looking for is in the array. So having a base case for not being able to find the element in the array is easy, right? We can do that right off the bat. I can say return nil if array.length is 0. So if I ever break my problem down into pieces so small that the array doesn't exist, so the length is 0, then I know that the thing that I'm looking for doesn't exist, right? Just like when min and max swap places, we know that the subarray that we're interested in is not there. We know that if I pass an array of length 0 into this binary search, then I know that the thing that I'm looking for is not there. So we can, at that point, return no. Okay? And now what we want to do is I still want to look in the center, so I still need to define mid, and I'm just going to say array.length divided by 2. And actually, once I wrote that, some of you guys might be thinking to yourselves, so wait a second, that's a different calculation of the midpoint than we did before. So if we look simply at the either the first loop or the first recursion of this function, I've actually defined mid in two different ways. So mid here is the length of the array divided by 2. However, mid here would have been the length of the array minus 1 plus 0 divided by 2. And so you might be thinking, wait a second, like, are both of those valid solutions to this? And the answer is yes, and I want to quickly show you why. And it's because we're using integer division. So let's look at a situation where I have 3 elements in an array first. Okay, so I have the iterative function that solves this by using the min and the max index and dividing those by 2. And then I have the recursive function, which I've decided to just take the length of the array and divide by 2. So in the iterative version, I have the min index of 0 plus the max index of 2 here, and I'm dividing that by 2 to give me the mid index of 1, which is the only viable solution for this because this array has an odd length. Therefore, there's only one midpoint that I can calculate for this mid calculation to be correct. The recursion takes the length of the array 3 and integer divides by 2, which gives me 1 as well. So those are both correct. So let's increase this to a size of 4 and see how these actually differ. So now I have 2 valid solutions here. Because this array is not able to be split up exactly, I can either choose this or this as the midpoint. So index 1 or 2. And this is where these two calculations, they just choose different ones, right? So one of these will choose the index that makes the shorter side on the left-hand side, and the other one will choose the index which makes the shorter side on the right-hand side. But both of them will choose a valid index for the midpoint. And it's just the nature of our integer division, and it's which number am I dropping the decimal from. As long as those odd numbers arrays give me the same answer, which they do, because these will always, the recursive side using the length, it will always round down to the actual mid element, then I'm good to go. But let's actually do this just to prove it. So the iterative version, I have min index of 0 plus 3 divided by 2, and that gives me 1 again using integer division. So that will give me this one, which is a valid midpoint for a length of 4. And then my recursive one, I take my length of 4 and divide by 2, and that gives me index 2, which is this one, but it's also a valid index for splitting my array in as close to half as I can. So that's why the calculations are different. It doesn't matter which one you use. I decided to use both of them just to kind of show you that. But they're both valid. Cool. So calculate my midpoint, and now I have to determine how to recurse here. So remember, the goal is to break my problem into smaller and smaller pieces until the problem's so easy that I can just solve it. So, and that problem being so small that I can solve it is this right here, but I need another base case where my problem is easily solvable. And that's the case where the array at index mid is equal to the element that I care about. So if the array at index mid is equal to the element I care about, there's another base case. I return mid at that point. Okay, now I still have to deal with the 2 other cases that I dealt with up here, where if the thing that I'm looking for is not right in the center, I have to choose to either pick the right-hand side of the array or the left-hand side of the array and continue to look at those portions. So if the thing I'm looking at in the center, just like we did before, if it's bigger than the thing that I'm looking for, so the thing that I'm looking for is smaller than the thing in the center, so I need to focus on the left-hand side of the array. So instead of redefining some max variable like I did in the iterative solution, I simply pass into binary search, recursive, a smaller portion of this array, a broken down subarray. So I care about the left-hand side of the array, so I slice it from index 0 all the way up to, but not including, the midpoint of the array. And then I pass in the element that I'm looking for. And I actually want to return this from the entire function. Because even if this function call doesn't find what I'm looking for, it'll call itself again, and maybe that one will find it. And if it doesn't, it'll call itself again, and maybe that will find it, right? But I'm returning, once this has called itself as many times as it needs to either find the element or find nothing, then all the returns are going to hit one after the other. And this will be the last return to happen if this is the line of code I hit in the first recursion. And we'll take a look at that on the whiteboard after this, just in case it's giving you a hard time. All right, and now at the end of the day here, I'm actually going to write this with a small bug, and then we'll talk about why it's a bug in a second. So I'm going to say return binary search recursive, And so remember, this case is capturing the ones that these two don't, and the only thing left is that the thing that I'm looking at in the center is smaller than the thing that I'm looking for. Thus, I need to focus on the larger right-hand side of the array. So that means I need to pass back into my binary search recursive array split from index mid plus 1 all the way up to and including the last element, and then pass in the element that I'm looking for. Now, I have a few problems with this that won't make this work right off the bat. It's very close, but it's not quite there yet. All right. Thing number one that will make this not work is that binary search recursive will return, when it does find what it's looking for, it's returning the index relative to the array that was passed in. So if I keep changing the size of the array that's passed in, that might affect the relative index at which my element is found. And this is truthful when, especially when, well, only when I am splitting from the center of my array up. So here, if I find, let's say I just do one recursion, and the one recursion was the left-hand side of my array, because I'm starting at index 0 and going to the midpoint, it doesn't change the relative indices of this subarray. Like if I find my answer at index 1 here, that would be the same as index 1 here because I just took the left-hand side of the array, and the relative indices of this left-hand portion are the same as the relative indices of the left-hand portion of my original array. However, if I pass in an array sliced from the midpoint up, and let's say I end up finding my answer at index 0 of this sliced array, I don't want to say that my answer is at index 0 because index 0 of this larger array is index mid plus 1 of my original array. So I have to compensate for the relative indices that this recursive call returns relative to the original array that was passed in. So we already kind of know what to do here because I said if we find this at index 0, we can easily tell that that was index mid plus 1 originally. So all I'm going to do is save the return value. Actually, I'm not even going to do that yet because that's the solution to my next issue. So what I can do is just say mid plus 1 plus whatever the relative index was. So like I said, if I find it at index 0 here, that was really index mid plus 1 of the original. So I just add mid plus 1 to whatever index was found here. But I still have a problem. That problem is that binary search recursive can return one of two things. It can either return an index number, so an integer, or it can return nil. And I'm not accounting for that with this line of code. I'm not accounting for the fact that nil might be returned here, and that would be what I would want to be returned from this return statement. I would also get an error if it returned nil here because I'd be trying to add numbers to nil. So what I need to do is account for the fact that if nil's returned, then I need to return nil here, and I don't want to try to add nil to some numbers, okay? That's a non-issue here because I'm directly returning the return of binary search for reasons discussed previously. And that's not an issue here because if I'm finding the thing I'm looking for, it's impossible for me to have returned nil. So what I want to do is I'm going to just save the response or the result of binary search recursion here, and I'm just going to return one of two things. If res.nil, if res is nil, go ahead and return nil. Otherwise, return mid plus 1 plus res. So now I'm taking into account, okay, so res might be nil. If it was nil, it means you can't find what you're looking for. I no longer care about calculating indices, so just go ahead and return nil. Otherwise, if it did find what I'm looking for and did return a valid index, compensate that relative index from this subarray and make it the correct index for the overall array that was passed in to this function. Okay, so this should be accurate. I think this will work. So let's go ahead and give it a shot, and then let's talk about recursion and how this works. We can draw it out and take a look at that. So I'll go ahead and copy this portion of the code right here, and let's say binary search recursive. And I really want to make sure that I change all this. I hate copying and pasting because it's so easy to forget something and you're not actually testing what you think you are. So I'm going to say result of binary recursive search, binary search recursive, search array, search num, those are good. Resbur instead of resb, search num is fine. Resbur instead of resb, and then finally resbur. So I'm changing all my variables to be the result of binary search recursive. I'm making sure to call recursive. That should be good. So let's go ahead and run that. And I'm getting the same answers. So that looks like it's working pretty well. All of them couldn't find it. All of them found it at the same index. Could not find it for all three. Could not find. Found at same index. All right, this is looking pretty good. All right, cool. So I think that we have working solutions. So now let's take the time to get some visual indication that my binary search is way better than my linear search when I'm looking through a sorted array. I'm not going to use any extra tools to determine the exact runtime or computation operations that are performed. We're just going to take a look at this visually because we talked about in theory why there were less operations performed, so I don't think that we're going to get anything extra out of doing it with extra time and extra coding here. So let's just look at it visually. And what I'm going to do is increase this to a size of, let's do 100 million. So 100, 1, 2, 3, 1, 2, 3. I think that's right. 1, 2, 3, 1, 2, 3, 100 million. And also what I want to do now is, because this is actually going to take a while to sort, I'm going to allow myself to use that same array over and over with different search nums, so I can test it a few times with different search nums to make sure everything's working well. So what I'm going to do is I'm going to say input equals gets.strip. I'm going to do a while input does not equal exit. Basically what I'm doing here is allowing myself to type in exit to end this infinite loop here that would not really infinite, because if I type exit it will break. So I have a while loop here that will break if I type in exit, and until I type in exit it's just going to, it's going to tell me, actually let's say gets ready. So, or sorry, not gets ready, puts ready. So puts ready. Once it's done sorting, it's going to tell me it's ready. It's going to wait for me to type something. As long as I didn't type exit, it's going to perform this test, and then it's going to allow me to redefine input and potentially either type exit again or just type enter or anything else really, and it'll go through the test again with a different search num. So this should be a good way to test it out. So let's go ahead and run this. And while it's sorting that 100 million elements, let's go ahead and talk about what I want to do before we end this. So I actually do want to do one more thing after this, and I want to show you how we can use binary search, the binary search algorithm, in a more flexible manner so that we don't force our users to use an array of elements here, or sorry, array of integers here. So right now we are bound by the rules that the only way I'm going to return our the midpoint right here is if these two things, the element I'm looking for and the thing in the center, if they respond appropriately to equals equals. And then the only way I'm going to look on the right hand side of the array, sorry, the left hand side of the array here, is if these two things right here respond appropriately to the greater than sign. So I'm really restricting myself to integers and floats and strings, and any complex, maybe custom objects that I've written are not going to be able to be used here because they don't necessarily abide by these rules. So what I'm going to do is allow my function to take a block, which is, if you're using a different programming language, it would be like a callback in JavaScript, or maybe a lambda function, which would be the same thing as a callback in Python. And really blocks are the same things as callbacks too. So what I'm doing is I'm going to allow the user to make the decision for me. Every time I look at a certain element, I'm going to hand it to my user and say, is this the thing you're looking for? And they're going to tell me yes or no. And they're going to tell me more than that. They're going to say, yes, that's what I'm looking for, and I'll give them back the index. Or they're going to say, no, the thing I'm looking for is to the right of this thing, in which case I'm going to do this portion. Or they'll say, no, the thing I'm looking for is to the left of this thing, in which case I'll do this portion. Right? So this is really cool because it lets them make that decision every single time, and it lets them use a lot more flexible or a lot wider range of things inside of their array, and lets them use our function in a lot more flexible sense. Also, another thing that's nice about it is that we now can pass in, and we'll do an example, and we'll see that we can pass in our own custom objects and use a block and make it work. So we're ready to go here, and I think it'll become more clear when we actually do it. So I'm going to stop trying to explain it without actually doing it. So let's go ahead and give this a shot. I'm going to click enter. All right, cool. So that was not the worst case scenario because we found it every time. Now, they were all successful. They found the same answer. There definitely was a pause after our linear search, with the binary search, both of them happening practically instantaneously. Let's try that again. All right, and that was the worst case scenario where it could not find it. So my linear search went through all 100 million elements and it could not find it. My binary search did significantly less checks than 100 million, and that's why those two popped up instantaneously. So if I keep doing this every few times, we'll see that there's always a pretty good pause after the index method, and then the binary searches are popping up instantaneously. The only time that there's really not too much of a visible change is if the thing that I'm looking for happens to be close to the left-hand side of my array, which was the case here. Cool. So let's go ahead and double this. And what we're seeing, what we want to see here is that the length of time index takes in worst case scenario approximately doubles, while there's no visible change to binary search, and that still continues to look instantaneous. So let's go ahead and do this and let it sort, and then we'll take a look. So I'm going to pause it so you don't have to watch it sort. All right, so we're ready to go here. So let's go ahead and click enter a few times and see what happens here. All right, cool. So not worst case scenario, but definitely about 2 times slower, I would say. Just a rough estimation. Okay, so there's the worst case scenario. Again, a few seconds for this to run as opposed to about a second before. And then these two are still happening instantaneously with no visible indication of any change here. So I think that's pretty good demonstration is with the tools that we're using, which are no tools. And so let's move forward from this and really quickly show how to make this flexible enough to use with something other than just an array of primitive elements. So let's start with the iterative version, and it's going to be relatively similar to what we already have. All we're doing is we are basically, we're almost acting, this function's almost acting like a contractor. So the user is contracting our function and saying, hey, I know how my elements compare to each other, and I know what I'm looking for. I'm contracting you out to search through them in the correct order, so I only do log n checks rather than me going through all of them. So I know that you know how to correctly do log n checks. So every time you take some element you want to check, bring it to me as the user, and my block will tell you if that's the thing I'm looking for or if I want to look at the right or the left-hand side of the array. That's kind of the intuition here. So we're going to do binary search iterative with block. Not the greatest name, however, that's not really what we're focused on right now. So now I'm only going to pass in the array here because if we're going to hand back to the user the midpoint every time, they already know what the element is that they're looking for. They don't have to give it to us. We're not using that anymore to make a decision. We're just passing them the midpoint of the array. So it'd be silly for them to pass us the element and then for us to pass it right back to them. All right, so really we're gonna say, hey, give us the array, and then when we have something that we want you to check and tell us what to do, we'll bring it to you. You already know what you're looking for, so just use it in your block. All right, so the logic needs to be the same so far, so let's put our end in there so we don't forget it. And we're gonna say the max equals array.length minus 1. The min is still gonna be 0. And while min is less than max, all of this logic stays the same. Sorry, less than or equal to max. All this logic stays the same. And now this is where we start getting a little bit different. So actually not quite yet. So let's calculate mid is min plus max over 2. Okay, so now is where things get different. I'm not making the choice right now based off of the middle point in the element of where to go or what to do. I need to give it back to the person who gave me a block. So I'm going to say the result of their callback or their block is going to be when I yield out to them. I'm going to yield to them the midpoint of the array, and they're going to tell me one of 3 things. Yes, this is what I'm looking for. Look at the left-hand side of the block instead, or the array instead, or look at the right-hand side of the array instead. So we have to figure out basically the contract we have with them so we know what they give back to us, what that's actually telling us. So pretty commonly what you'll see for things like this is returning a negative, 0, or a positive. This is used a lot in sorting algorithms where, like, if you're handed 2 elements, A and B, you'll say like you might return like A minus B. So if A and B are identical, then you'll get back 0, saying hey that they're the same. These are, this is given that A and B are integers or strings or not even strings, so integers or some sort of number. So this would be the very primitive implementation of this, but we're just going to talk about it for the intuition now, and don't worry, we'll take a look at what happens when the array is objects. So basically what I want to do is have the yield, when I yield this, where did I write this? Okay, here, oh, here we go, sorry, it was right there. So when I yield this midpoint of the array, I want them to give me back a negative number or a 0 or a positive. Now 0 is the easy one. 0 is indicating that the middle of the array, the element, the middle of the array, and the thing that they're looking for is the same. So if they give me back 0, then that is an indication that that's what they're looking for. So at that point, I return mid. However, now we have to determine what we want to get back in relation to which portion of the array we need to look at now. So let's say that they follow this kind of convention that you'll see a lot. The thing that we give them minus the thing that they're looking for. So if the thing that we give them, so the middle portion of the array, if that value is greater than the thing that they're looking for, this thing will return a positive number. And if the portion in the middle of the array, if the middle number is larger than the thing that they're looking for, that means that we need to focus on the location in the array where things are smaller, which is the left-hand side of the array. Okay, so if they return a positive number, so if the thing we give them is too big, so if res is greater than 0, if the thing that we gave you is too big, and we need to focus on the left-hand side of the array, we now need to do this logic right here, where we need to focus on the left-hand side. We'll redefine max to be mid minus 1. Okay, and then else, we don't need to worry about putting any logic there because the only thing left is that res is negative. Okay, which means that the thing that we gave them was smaller than the thing that they're looking for. So something smaller subtracted by something larger is a negative number. So if they give us back a negative number, that means we need to look at the right-hand side of the array, and thus we'll redefine min to be midpoint plus 1. Okay? Now, to be good programmers, we could make sure that they pass in a block, either by putting in a if statement, so if block given, something like that, or we can specify it in the argument list here by saying ampersand block, and that will say make sure that they give us a block and then convert that into a proc. Okay, so let's do that for now. Let's say and block here, making sure that they pass in a block. And to test these, we're actually going to go back down to a very small array size. We'll go back down to 2,000, so we don't have to keep waiting for it to load as I keep testing this. And let's go ahead and grab our binary iterative and paste it down here. And make sure input, or redefinition of input happens at the very bottom. All right, cool. And then we'll put a puts for some space here. So we're going to say binary search iterative block. Another O of log n, binary search iterative block, so resbib. We're going to stick right now with numbers, okay? And then we'll change it to be something that would be more pertinent to the example of like why we actually did this in the first place. So maybe some custom objects. So let's change this to redbib. Make sure we call the function binary search iterative with block, and we no longer need to pass in the search num. And let's actually not put a block right now to test my theory that we get an error if I don't put a do end block here. So if I don't pass in a callback, I should get an error. So let's test that out, make sure we do get that error. But let's also change all these things to resbibs. Perfect. Resbib. Search array, resbib, calling the correct function, calling it the correct variable name in here. All right, that should be good. So what I'm hoping for right now is an error saying you need a block. Awesome. So no block given. Perfect. So the way that I put the argument list, it does require this callback function or this block if you're doing in Ruby, which we are. And I get back my mid value. So now what I'm going to do, and it's pretty common in Ruby, let me open up an interactive terminal real quick and we can take a look at this. So instead of saying midval minus search num, which would work, we're going to use, we're going to be a little bit more Ruby-y and use the spaceship operator. All the spaceship operator does is it takes the sign of that subtraction. The sign operator is basically saying if it's a negative number, turn it into -1. If it's a positive number, turn it into +1, and if they're equal, turn it into 0. So if I had my left-hand side was 3 and I was subtracting 3,000, obviously I'd get a negative number. But if I did the spaceship operator, it would just be the sign of that, which is -1, right? Conversely, if I said, some larger number, spaceship operator 3,000, I get a +1, as opposed to the subtraction, which would give me a large positive number, right? And then if they're equal, 3 and 3, here both the spaceship operator and the subtraction would both give me 0. So we're going to use the spaceship operator here, and I'm going to say mid-val spaceship operator of search num. And right now you're probably thinking, hey, this seems like more work because now we have to do stuff where I didn't have to do stuff before. And that's true in the case of us only using an array of integers here. But again, let's go ahead and do it this way so we understand what's happening, and then turn it into something that our previous functions would be unable to handle, and kind of explain why it's better. So let's run this, make sure it works. All right, cool. So we're finding the same answers. This is great. Awesome. Perfect. So it looks like that's working just great. And we're not going to change this to a larger number. We will at the very, very end, just to see that we're going to have 4 binary searches and they're all going to fire off super, super fast. And this one's going to be slow. But we'll see that one more time at the end. But before we do that, let's go ahead and actually make this work in a way that wouldn't really work with the other method. So what I'm going to do is I'm going to change this search array. Let's say we were in a situation where we had more complex objects that we were working with. So I'm going to take my search array and I'm going to map it to some sort of data wrapper. So we have our, this is a very obviously contrived, simple example, but we might be in a position where we have complex objects that are sorted by some sort of characteristic, and I want to keep them as objects, and I want to get the whole object at some point. So I don't want to just map them to a specific characteristic. I want to find them by that characteristic, but then I want the whole object back. And previously, what I would have had to have done is map this search array or this search objects from the data wrapper to some piece of data that they're sorted by. And then I would have to perform binary search on them, get the index, and then go back to the original array with the objects and retrieve the whole object. That's very counterproductive because mapping them is an O of n algorithm. So if I have to map it before I use binary search, what was the point of using binary search at all, right? Like using that log n algorithm, if I have to map it first every time, which is an O of n algorithm, it nullifies the necessity for, I might as well just use linear search instead of mapping, right? It'd be faster. So what I'm going to do is, now that I have this block where the user can just tell me which way to go, I can now achieve O of log n search time with objects. So I'm going to have this search objects, and I put it outside of my while loop so that it will happen, and it will maintain just like the search array. And the search num now, I'm also going to have a search object that I'm looking for, which is just going to be a data wrapper. And you might be like, what is data wrapper? And don't worry, we're going to write it. .new of search num. So basically, again, this is a very simple example. They're obviously not complex objects, but basically I'm just showing you that I can have some sort of custom class that is wrapping some piece of information. All right. Data equals data, and then attribute accessor data. All right, cool. So now I have this class data wrapper that's wrapping some piece of information, and I can binary search through this array of data wrappers and searching for a specific data wrapper object based off of the data that's inside of it. Okay, so now what I can do here is, instead of looking through my search array, I really want to be looking through search objects, and I want to check to see if the mid-val's data, how that relates to either search num. I could do that, or I could say my search object.data, right? So that means that I could be searching using another object, or I could just be searching with search num. Let's actually do that. That's fine. I can show you that I can, if I have an integer that specifies a piece of information inside of an object, one of the object's instance variables, as long as those objects are sorted by that characteristic, I can relate that characteristic of an object that I'm getting back by the primitive information that I already have that I know I'm searching for. So let's go ahead and do that. Let's make sure I changed everything correctly. I'm still using the with block method. I'm looking through search objects now. I'm getting back one object at a time. I'm relating it to the search num, and I'm using resbib here. Could not find search num. All right, so now here I'm getting back a data wrapper object. So let's call .data on whatever I get back. And actually, let's not call .data. Prove that it is a data wrapper object, and then I'll call .data on it and show you that it's the right number. Actually, you know what? Let's do this. Let's be even better. Let's go ahead and say def to s. All right, and I'm going to say, so when I print out this whole object, I'm going to get I am a, and then we'll say data wrapper, but I'll say self.class just to be fancy. So I'm a class with data of, and then I'm going to pass in @data. All right, cool. So now when I print out this whole object, I should see that it is in fact an object. However, it has the same number in it as all the other ones. Binary search, iterative block, O of n, found 141 at index. What is happening here? Give me 1 second. It looks like I'm getting back an integer. Maybe I had .data there. So it's finding the right thing. Iterative block, search array. That's why we need to look through search objects. Okay, sorry about that. So that's why I hate copying and pasting, right? Good. Don't do what I do, right? Learn from my mistakes. Don't copy and paste. All right. So, all right, there we go. So now that I'm actually looking through search objects, which I was searching for originally, so I can see now that my resbib returned the index of an array of objects, custom objects that don't know how to compare themselves with equals, equals, less than, greater than, etc. And it was able to return the index where an object lived with the data that I was looking for. So it found I'm a data wrapper with a data of 1711, which is exactly correct, at index 1725, which is correct. Okay, so that works great. And let me show you real quick what would happen if I go into my other iterative one and I pass in search objects, and search object, right? So I'll pass in the object as well. We'll see that this breaks. You can't do this, right? Undefined method greater than for data wrapper. And so it didn't even care about what this was yet, because it like the equals equals actually didn't cause an error. It's when I try to say, is one data wrapper greater than something else? It doesn't matter what that something else was. It didn't know how to perform a greater than sign on a data wrapper. So that breaks it completely. So by allowing the user to do something a little bit more advanced here, it greatly expands what they're able to use our method for on. So let's change this back to something that doesn't break. Search array, search num. And let's really, really quick do the same thing for our recursive. And the reason I want to do it for the recursive version too is because there is one little trick that you have to do to be able to recurse with something that takes a block. So it's not that hard. So binary search recursive with block takes in just the array. It doesn't care about the element because now the user's in charge of that. We keep the same logic, return nil if array.length is equal to 0. Our midpoint calculation is going to be the same of array.length over 2. And now we say if, okay, so now we have to say if some result that they give back to us, so let's define that result, is equal to yielding out array at the midpoint. So if the result is 0, right, just like last time, if the result is 0, return mid. Perfect. Now remember, if the result is positive, it means they want to look at the left-hand side of the array, right? So that result being positive is the same else if as if we were doing this line 52 right here. So we're going to say else if res is greater than 0, then we want to return binary search with block, or sorry, rec with block. And we're going to pass in the subarray that we care about, array from index 0 up to but not including the midpoint. And now we want to actually pass into that recursive call the proc, right, which is just an anonymous function. We want to pass in basically the block that they pass to us. So we want to make sure that this recursive call gets the same block that they called here. Okay? And then else covers the fact that they want to look at the right-hand side of the array. So, and that's if res is negative. And so here we're going to do the same logic. Res equals binary, Actually, let's not call this res because we're already using res. So we're going to say binary search res, BSR, is equal to binary search recursive with block array. And now we're going to go from the midpoint plus 1 all the way up to and including the last element of the array. And we're going to also pass in the block here. And the ampersand, guys, and let's put the ampersand block here too to make sure that it's passed in. It just turns something into a proc, right? So it's going to make sure that that block is a proc, anonymous function. All right, so so same logic, right? So now we say we return return what? Well, if BSR is nil, we want to return nil. Otherwise, we want to return the midpoint plus 1 plus BSR, just like the same logic before. So that should work just fine. Let's do that horrible idea of copying and pasting again. And hopefully this time we catch everything. And we're going to say binary search recursive block. Let's say with block. That's a little bit better. I don't know why. I didn't do that before, so all of log n. Okay, so res brb binary recurse with block search objects midval.data. This can be all exactly the same. So to the user, it's inconsequential whether we're using iterative or recursive way to solve this problem. It's completely transparent to them, except for the fact that we named them accordingly. But obviously in real life, we just call it binary search, right? And then it would be completely transparent, the method in which we're using to solve that. And then we say, okay, puts res brb.nil, could not find search num, otherwise found search objects of res brb at index res brb. All right, cool. So that should be good. We just to look over real quick, so we included that there. We're passing it in there. That should be fine. So let's go ahead and ramp this up again to 200,000 as a last check. Actually, let's do it with 2,000 just to make sure it works, and then we'll go ahead and we'll. All right, cool. All of them couldn't find it. All of them found 1482, 1583, 1800. This looks great. So let's do one last thing. Let's ramp it back up to 200 million. 1, 2, 3, 1, 2, 3. Is that right? 1, 2, 3, 1, 2, 3, 200 million. Yes. So 200 million. I'll let you guys pause out while this sorts, and then we'll just make sure that the linear search takes a long time and all the binary searches are instantaneous. All right, cool. We're ready, and we're ready to test this last portion. So let's click enter. All right. So we can see Ruby index is taking a long time, and hopefully binary search, all 4 of them will pop up instantaneously. There we go. All right, so worst case scenario, it couldn't find it. All 4 of these happen instantaneously. So awesome asymptotic runtime, super, super fast and flexible so that people can use it on something more than just numbers and strings. We can actually use it with our own custom objects when we add the callbacks and the blocks. Perfect. Thanks for tuning in, and I'll see you guys later.